First section is on the development of a semi-analytical modeling approach for fracture initiation and the optimization of that using oriented perforating. It's a well-known concept that the orientation of fracture initiation, what is known as the PFP or the preferred fracture plane, is solely dependent on the trajectory of the wellbore with respect to the subsurface in situ stresses. For horizontal wells drilled parallel to SH max, which is the maximum horizontal principal stress, the PFP is oriented longitudinally to the wellbore. Longitudinal fractures are ideal for frag and pag operations and formations of moderate to high permeability, whereas for wells drilled parallel to the minimum horizontal principal stress SH mean, which is the current industry practice and even a state law in Louisiana, the PFP is oriented transversely to the wellbore. Transverse fractures are ideal for low permeability tight formations such as shale. As I mentioned during my general exam, the presence of the wellbore itself disturbs the stress field surrounding the wellbore such that the orientation plane of the induced fracture initiation is not guaranteed to follow the PFP. Propagation of fractures which initiated along a non-PFP orientation is not sustainable. This is because as the fractures move away from the wellbore, the level of disturbance that the presence of the wellbore imposes on the stress field diminishes, encouraging fracture propagation only along the PFP. As a result, fractures initiated along a non-PFP orientation, for instance longitudinal fractures initiated from a well drilled parallel to SH mean, will either terminate prematurely or forced to reorient to align with the PFP, which for this well trajectory is transverse to the wellbore. This generates tortuosity in the near wellbore region, which can have significant completion-related consequences, such as early screenouts and fracturing fluid leakage along the well, as we see in this microseismic schematic here. This yields to production-related inefficiencies, such as poor well performance following stimulation, adversely impacting the net present value of the project. Besides the orientation of fracture initiation, a second dependent variable is the fracture initiation pressure. During a stimulation treatment, practitioners monitor the pressure from the surface. As fracturing fluid is pumped downhole, the pressure increases at a constant slope with respect to time. Then the slope starts decreasing as the fluid starts leaking into the pores of the surrounding formation. The point at which this starts happening is known as the leak of pressure, or LOP. As the fluid continues to be pumped, we reach a point where the pressure drops dramatically. This is the formation breakdown pressure, or PB, which is the highest pressure reached during a hydraulic fracture treatment. Despite the leak-off and breakdown pressures being distinctly observable from the surface, it's really hard to pinpoint the exact fracture initiation pressure. Fracture initiation occurs within the yellow shaded region between the leak-off pressure and the breakdown pressure in what I would call, for practical purposes, the fracture initiation window. All three of those pressures are interrelated, and it's to the practitioner's objective to keep as low as possible in order to minimize the amount of horsepower necessary for the treatment, which is directly proportional to the number of trucks needed on location. As I also presented in my general exam, we set our horizontal wellbore parallel to SH mean and orthogonally to the vertical overburden stress SV and the maximum horizontal principal stress SH max. The stresses in the near wellbore region are given by the Kirsch equations from 1898, which were later modified by Hubbard and Willis for linearly elastic media with static pore pressure. The Kirsch stresses on the wellbore radius act in the configuration which I show here in cylindrical coordinates. We have the blue axial stress sigma YY, the red tangential stress, also known as hoop or circumferential stress sigma theta theta, and the green radial stress sigma RR. What I don't show here is the shear stress, which is 0 on the wellbore radius. In the dissertation, I used magenta color for the shear stresses. For perforated wells, we follow the Hossein method published in 2000, performing a second Kirsch analysis on the perforation tunnel. This allows using the wellbore axial and tangential stresses as inputs. This allows us to derive a mathematical expression for sigma theta theta p, tangential stress on the base of the perforation tunnel. The value of the sigma theta theta p orthogonally to the wellbore is the stress we need to overcome in tension to generate longitudinal fracture initiation. We'll call this the longitudinal fracturing stress sigma theta L. And similarly, the value of sigma theta theta p parallel to the wellbore is the stress we need to overcome to generate transverse fracture initiation. We'll call this the transverse fracturing stress sigma theta t, as shown here by the blue arrow. I did modify the Hossein approximations for the two fracturing stresses to incorporate pore pressure effects, and that was my first contribution. To assess the validity of the modified Hossein expressions, I built a numerical model in FLAC 3D, which I call True Three-Dimensional Numerical Model, which was described in more detail at my general exam and in chapter 4 of my dissertation. FLAC 3D is a finite volume simulator which uses stress and strain boundary conditions. This is the mesh of my model, which involves a 1/8 block model showing a wellbore going through, intersected orthogonally with the cylindrical perforation of smaller radius. The relative geometric dimensions are shown here. Utilizing the true three-dimensional numerical model to calculate the longitudinal and transverse fracturing stresses against wellbore pressure for the parameters of the Barnett shale, we see that the exact numerical solutions are quite different than the modified Hossein closed form analytical approximations. This is both for perforations in the direction of SH max and perforations in the direction of SV. The solid lines show the modified Hossein approximations, while the points show the exact numerical solution. Nevertheless, despite the discrepancy, the situation is not terrible. We can easily tweak the analytical expressions to make them